Today we are going to continue with a technique, and the advanced technique in digital signal processing called a short-time Fourier transform. I'm not going into too much detail into that, and I need to say beforehand that I will not cover everything of the short-time Fourier transform in the final exam. But I think this is a very important concept and a very important technique in signal processing. So I would just like to open the door for us to understand what is going on concurrently in the field of digital signal processing. And the concept is very straightforward. I'm trying to explain the idea, the basic idea today. So if you have any questions, feel free to send me a chat or just stop me by asking questions. I'm sure many of you will have the similar questions as well. Okay, so let's start. The topic is called short-time Fourier transform. Short-time Fourier transform. So the short-time Fourier transform, STFT, it divides a longer time signal into shorter segments of equal length and compute the Fourier transform separately on each shorter segment. So what does that mean? Well, usually when we calculate the Fourier transform or doing the signal processing, we need to collect the entire stream of signal. And then we do it all together using a Fourier transform or using any transformation, Z transform, doing that. So it has a delay. You have a delay that you collect all the signals. This is one problem, right? You have to wait for a long time and collect all these signals and doing one shot and doing a Fourier transform. The other problem is that now if you are going to collect the entire signal, and you cannot guarantee the signal, the frequency will not change. If it's a static signal, I can collect it thinking that the frequency component does not change. I calculate the Fourier transform. But the chances are that the signal is going to change. For example, if I got a draw here, if I have a signal look like this, here is in time. So the signal is a wave that becomes denser and denser, denser and denser. Okay. So when you calculate the Fourier transform of the entire thing, it is different because the frequency at this part, if you calculate just this part, the frequency will be lower than if you calculate the frequency from here to here. So the frequency actually is a frequency sweeping signal. The frequency is going higher and higher. So we are not going to capture the localized information, the localized in time, if you compute the entire signal using just one Fourier transform. So in this case, we think, well, can I just calculate one segment by another segment in time? So what we are trying to do is we are having the signal here in time, and I'm going to calculate only a segment. And using this segment, it's a short period in time, relatively it's a short period. I'm calculating Fourier transform. And then we get its frequency domain picture. In the picture here, it's kind of, we set it up. It's the vertical axis is my frequency domain. So this is one of the signal. And then I switch, or I shift the window from here to here, and I capture the next segment, short time, doing a Fourier transform as well. And I capture the frequency signal here and calculating a Fourier transform according to this short period. And then I will have a group of those frequencies in the time domain. I have a group of those frequency signals. Well, how to do the shift in this time doing different segments? Now we know from the windowing I ask you to watch is that I can simply do a window. So if you just truncate the signal, we are doing a window which is a rectangular window. Now we know we can do many different kind of windows, right? We can using a look like a Gaussian window. We can use a raised cosine window. We can use a Hamming window or hand window. But anyhow, we are doing a window called GT. So this signal here in this segment is my original signal xt. Windowing. Windowing is a product in the time domain times gt. Okay, if it aligned, so gt, and it's right here. The next segment, suppose here, that will be xt times gt subtract tau. You have a shift. The window has shift. And then I take this signal, xt times gt, go through an FFT. So I will have a frequency signal. And then the output of this will be a collection of those frequency domain signals. So if I plot together, I have a 2D output. One dimension is in time. Now this time is time that I shift my window. It's tau. And then here, another dimension is frequency, of course. That's frequency f. So you will have this picture. It's a 2D output. Actually, it's 2D output for each pixel of this 2D. You will have a value, which is FFT value. Let's look at the continuous time, short-term Fourier transform. With a sliding window, window is WT. And as we put in the picture, that's our GT. The short-term Fourier transform signal is given by that. Well, if you do a Fourier transform, now, as we said, we are doing a Fourier transform on this windowed signal. This is signal xt, go through the window gt. And this is a sliding window with a sliding, that's a time delay or time shift of tau. So this windowed signal looks like that. And doing a Fourier transform, so multiply by e to the negative j omega t and integration dt. G tau is a window function. For example, it can be a hand window, Gaussian window, centered at a 0. And then we have capital X is a Fourier transform of this windowed signal. As we said, it depends on two variables. One is, of course, that's a Fourier transform, so it's a function of frequency omega. It also a frequency of the window shift, which is tau here. So that's another, it's a time tau, frequency omega. Capital X tau omega is two-dimensional, with tau being the time axis and omega being the frequency axis. Now this time tau is different from time t here. Right? This is the time that we shift in the window. We cut for the short-time Fourier transform. Tau is called the slow time with respect to the high-resolution time t. Sometimes we call t, that's a fast time. That is the time that we use that for the Fourier transform. We use that time to find the variation with respect to this t that I showed the frequency. But tau is slow time. That is the shifting of this short-time window. So we write out this short-time Fourier transform formula again in the box. This is a short-time Fourier transform. Now, if I have a discrete time short-time Fourier transform, we know we change the integration to a summation. Then the time index t becomes a discretized n. N is an integer. And then this kernel, for Fourier transform, this kernel becomes, that's a e to the power to the negative j omega n. So we change n here, but we keep omega. So what we imply is in the frequency domain is still continuous. Continuous in frequency, but discretized in time. And then we will have this time shift is also discretized as integer of m. So we have this summation for discrete time short-time Fourier transform. Well, m is discrete and omega is still continuous. Omega is the frequency. In practice, we use discrete short-time Fourier transform. In practice, we actually use discretized variable for both time and the frequency. Also in practice, the entire value will be quantized, right? So everything is discretized. We have m and k. This is my variable. So m is the time shift. K is the discrete index of frequencies. So the entire formula for short-time Fourier transform is very easy to understand and to remember. Everything is a Fourier transform. We know that if you take any signal, you multiply by this kernel, and then you do either integration or summation. You do either continuous time or discrete time Fourier transform. The only thing we know is that this part is a windowed signal. That's it. It's a windowed signal. So that's a short-term Fourier transform. The output of the short-term Fourier transform, if I only take the absolute value square, which means we only take the amplitude square, we neglect the phase term. Now for the short-term Fourier transform, again, the output will be a complex number. X is a complex number. So it has both the amplitude and a phase. If we neglect the phase, only taking the amplitude, we call that a spectrogram. Fourier transform, we call that spectrum. Here we call that spectrogram. A spectrogram here is square magnitude of the short-term Fourier transform output. So the spectrogram of the signal xt, it is a function. It's a two-dimensional function. It's a function of tau and omega. So I write it expressed in this way. It is that's absolute value of capital X squared. So we have a picture here at the bottom. This is a spectrogram using the color code. Now it's a real value, so I can use a color code to express that. Two-dimensional signal. Here is time tau. That's the shifting time, right, of my window. This is the frequency f. So we can see for different time, it gives me a frequency signal that it changes. The frequency is not static, it changes. And using this spectrogram, we can actually see a lot dynamic environment in the frequency. For example, at the very beginning, it's a short time. We windowed that. And I don't have too much in frequency. Maybe there's no signal at all. So everything is low energy with this cold color. And then if you look at here at the time about 0.25, we have some hot color here. It looks like we got, if you just look at this slide right here in this shifting tau, we see we got some low frequency component, especially we have some hot color right here. And then we got a few of here and here, maybe nothing is here. And then we change, let's say if we change to this time instant, another tau 2, this is tau 1, we see we got some hot color here at higher frequency, about 3000 hertz. So the frequency indeed changed. And we are using that to capture a dynamic picture of a spectrum, of a spectrogram. So you can imagine if in a practical system, this entire spectrum can roll out. It can shift as time goes by. It can shift because you are taking a short-term window and you take that all the time. And you don't have to collect or wait for all the signal coming in. As enough sufficient signal coming in, take a short-term Fourier transform. And then new data come in and you shift the window and continuously perform this short-term Fourier transform and get the spectrum result. And it will be a dynamic rollout spectrogram. Okay, so it's very nice. We can do many things using the spectrogram. For example, if I want to check the pollution of my spectrum, if I want to see if there's any of those interference in the environment, I can use the spectrogram to check the pattern of those interference, how they are regulated. And maybe I can find out some of the clean time instant for my use, for my communication, for some other use. People can also use a spectrogram. It's very popular in the radar system. In radar system is that I'm going to swipe the one angle of the space, and this frequency we can use a Doppler frequency. The Doppler frequency basically, if there is an object flying towards you, the Doppler frequency will be higher. If it's flying away from you, Doppler frequency will be lower. So you will see some frequency change. And using that, you can capture a dynamic picture of an object. You will see interesting thing if it's a hot color. That's something. If it's moving toward high frequency, you will know there's something just flying towards you. So it will be a very useful real-time tool when we check with the frequency environment. Here is also a picture of a spectrogram. Now this spectrogram is with with a digitized frequency and digitized time. Everything is digitized, time tau is digitized, frequency is digitized. So we see the spectrogram, instead of continuous picture, we have some small blocks. Each block is with a period with a digitized time period and with an index, frequency index. So it's kind of occupied a portion of the frequency. So we see those blocks. And this is more close to something that we see in a real digital instrumentation. And then if these blocks give you the resolution, you have a high resolution, and those smaller blocks will become smaller and smaller, consist of only a few pixels and showing a very nice spectrogram. Let's look at some detailed mathematics behind the Fourier transform. Particularly, we want to find out what's the relation between a Fourier transform, a general Fourier transform, with a short-term Fourier transform. How can we bridge between these two? So we look at a window function here, gt. Suppose that this window function is scaled. So we have integration of gt, or using this time index we use in tau, it doesn't matter. So with g tau, integration d tau, and this integration is 1. So what we have here is that, suppose this is my window function gt, or g tau. So the integration, which says that the area of this window function, below this window function, is 1. It's normalized. Now, since we are calculating area, it doesn't really matter where is it positioned. So you can change different positions, different tau. It's integration over negative infinity to infinities. And then beyond this window, it's 0 outside anyways. So it doesn't matter when you shift this shape. Which means that if I shift my window function, becomes gt subtract tau over d tau, it still gives me 1, right? For any time t. Now this change a little bit. Here, I'm kind of using this variable t for shifting, and using tau as this is frequency, this is time domain, which is tau. So integration over tau. Therefore, since this is normalized as 1, we can simply put this, multiply that to my original signal x. You multiply by 1, doesn't change. And then we bring this xt inside integration. So in integration, xt times gt subtract tau, d tau. Now this looks familiar, right? That is my windowed signal x. And then this window can shift by tau. So let's just keep it here. We know we have that. If you're doing this, that is the original signal xt. Fourier transform of xt. So in general, a Fourier transform can be written in this format. So we take a signal, multiply by its kernel e to the power negative j omega t dt. And then we use that to replace xt. This is coming from the previous page, right? That's the same. That's the same as xt. So I replace that replace xt with this bracket. The inner integration is integration over tau. The outer integration is integration with respect to t. Now we are doing a trick here, as we always do that. We swamp the order of those two integrations. Integration is linear operation, so I can swamp the order. I'm doing the integration with respect to t first in the integration, and then I do the outer integration with respect to tau. Because this signal, it's a function of t. Also here, this kernel e to the power negative j omega t is also a function of t. So I have to put in this inside my integration. So it's with integration with respect to t. And then outside is with respect to tau. If we look at this bracket, that is our short-term Fourier transform. This is for the short-term Fourier transform. So we are doing a Fourier transform on a windowed signal, right? So that's a short-term Fourier transform. So we have the final line here. This is how it related with Fourier transform. Now it makes sense. So all we have here is we got the output of a short-term Fourier transform. Then we just calculating over the entire shifting time tau. So each time you give me a segment of tau, if I want to see the entire effect in frequency, well, I need to add it together, right? So integrate all these together. So the general Fourier transform is a phase coherent sum of all the short-term Fourier transform of xt. It looks nice and it really makes a lot of sense of this. This is xt equal to that. The inverse Fourier transform. The inverse Fourier transform, in general, we got this formula. Xt is 1 over 2 pi. We just went over the window. Window is 2 pi. This is window Fourier transform. The frequency window size is periodic of 2 pi. Then the integration, negative infinity to infinity, x omega times e to the positive power j omega t d omega. This is our inverse Fourier transform. We know this part can be expressed as this coherent sum. So we have integration of capital X tau omega d omega and put it in the inside. Doing the same trick, we change the order of those two inner integrations, outer integration. So the inner integration becomes the integration of x tau omega e to the power j omega t, integration with respect to omega. It's a function of omega, it's a function of omega. Doing integration over 2 pi, then the outer integration is with respect to tau. Now remember, we have this line. We have this line of the previous two slides ago. So if you compare this with, if I put in this term, so we have here, this part should be equal to this bracket. Compare those two equations, right? Xt equals integration, this red box thing, d tau. So xt equal to this integration of this red box, d tau. Therefore, those two parts should be equal. And then we get xt times gt subtract tau equal to the things inside the red box. That's 1 over 2 pi integration capital X tau omega e to the power j omega t d omega. So we have that. And this is, of course, that is true because this part is short-term Fourier transform result. Short-term Fourier transform result xt. Now you do an inverse of that, you will get this windowed signal. This is my xt times the window function. It's shifted window, gt subtract omega. So indeed, this is the inverse short-term Fourier transform. So we are using a short-term Fourier transform. So we kind of doing it in a dynamic way. Every time I just taking a very local window in time, find its frequency components. And then because the signal is time varying, it changes. So I'm using that to track all this frequency change and by shifting this window. And then maybe we can take one step further. Now, once you give me a window, this window is the length of the window. Somehow it's fixed. It's fixed. The GT is fixed. What if I am thinking about a signal that, let's say, I'm using my original example here. The signal is going like this, okay, and going denser and denser, denser and denser. Okay, you got the idea. So at the very beginning, maybe this window is from here to here. That's good enough for me to calculate the Fourier transform. And then I would like, ideally, I would like the window to shrink, becomes relatively smaller and smaller and smaller in order to capture this detailed frequency change. Right? Because if you're still using the same window length from here to here, the same as from here to here, and then you may not be able to capture the frequency change inside this window because they just change too fast. in time to fast. So in that case, I also want to change the size of the window. And not only I want to take a short window, but I also want to change the size in the window. How can we do that? So people are smart. So we invented called a wavelet transform. So wavelet transform. Wavelet transform is a very popular signal processing, advanced signal processing technique that I use today. And in many signal processing, as we will see, we are using wavelet transform as a magnifier. This magnifier not only showing the signal to find the frequency, but also want to localize in time. So we can really use a wavelet as a very good magnifier to examine, to analyze signals. The concept follows short-time Fourier transform. It's easy to explain and easy to understand. Wavelet transform, WT, is another mapping from L to R to L to R square. Now, let me explain what this means. R is real. L2 is the L2 space. L2 is L2 norm. So you can think that as a Euclidean space. So Euclidean space, you check the 2 points in the space using the Euclidean distance, which is if I have a 2 point A subtract B in real, if I have a 2D, that is a vector A subtract B, but it's still Euclidean distance. Picture is that you're calculating the length of this vector between A and B. Okay, so that's Euclidean distance. So I'm using L2, it's L2 norm. And then it's the function in general, we have a function of one variable mapped to a function of 2 variables. So short-term Fourier transform is one example, right? The signal is signal of time. It's one variable. Then short-time Fourier transform output is a signal of both frequency and a shifting time, and tau and omega. So it's R squared. That's a 2-dimensional real space. Okay. The wavelet transform, one with the superior time frequency localization as compared with short-time Fourier transform. As I said, it's an extension of short-time Fourier transform, but it has a better time localization feature because you can really zoom in and zoom out in time. And the miscibility condition on the wavelet is needed to ensure invertibility of the continuous wavelet transform. So same as Fourier transform also have this admissibility condition. So some signal you have Fourier transform, some signal you don't. We know for Fourier transform, almost all the practical signal is admissible. However, for wavelet transform, it's not the case. So you really need to discuss what kind of signal you can take a wavelet transform, what kind of signal that it doesn't have a wavelet transform. But we are not going to get in too much detail into that. Suppose all the signals we have is a nice signal that we can do a wavelet transform. The discrete wavelet transform, DWT, is generated by sampling the wavelet parameters A, B on a grid or lattice. So here's the wavelet parameter A and B. Now what we had before, this is 2-dimensional. Therefore, you have a signal or the output with respect to 2 variables. Now we have with respect to omega and tau. And for the discretized short-time Fourier transform, this is continuous. For the discretized short-time Fourier transform, is respect to k and m. Those are the 2 integers. So in general, Fourier transform T. In general, I have a wavelet transform. It's also that output function is a function of 2 variables, which is called A and B. If it's discretized, then A and B is on a grid or on a lattice, and A and B is just those integer index. A fine grid mesh permits easy reconstruction, but with oversampling, a coarse grid could result in loss of information. So it's very similar to discrete signals, right? So if it's a very fine grid and it's close to continuous, it's very easy to do a reconstruction. But it's a coarse grid, you may lose some information. So the wavelet is, we are taking, why we call it wavelet, it's called a small wave. Small wave is wavelet. Now, if you think that this signal, let me draw here, x omega is doing x Fourier transform as xt e to the power negative j omega t dt, okay, integration negative omega. If you think this kernel here, when we're doing a Fourier transform, this is a cosine function. Cosine or sine in complex, it's just a cosine function. It has a negative part because you are doing a direct Fourier transform. But anyways, it's a cosine function, and this cosine function is has only one frequency. It's a wave, right? Its cosine function is a wave. It's a very long wave. So we have this cosine function. It's a long wave. Ideally, that's going from negative infinity to infinity in time. Now, as we said, we need to do a short-term Fourier transform. I cannot take time that long. And then shorter and shorter, I only have a very short wave, which is called a wavelet. So people invented wavelet. Instead of using the kernel here, which is a long wave, can I use a short wave? I'm using a very short wave to replace this. And this short wave can be in this format. This short wave can have this shape. It's called a Ha wavelet. So I only have those two rectangular function. One is positive, one is negative, using this. We have a Shannon wavelet, which is also a sinc wavelet. That is a sinc function. It's truncated sinc function. You can take a short period. We also have the Bauchi 4 wavelet, the Bauchi 20 wavelet, different format of wavelet. Gaussian wavelet is a Gaussian function, truncated. Biorthogonal wavelet in the real part and imaginary part itself is a complex number. So it's a biorthogonal wavelet. We have a Mexican hat wavelet. It looks like a Mexican hat. And a Coe-flat wavelet. And there are many different wavelets. So we are using this wavelet, and it's called psi t, to replace this long wave, which is in the regular Fourier transform. It's e to the negative j omega t. This is a long wave. We are using a short wave to replace that. So if you're using that, that means what is a wavelet transform? Well, that's simple, right? It's a wavelet transform. Something looks like that. It's an integration of xt psi t dt. And a psi should be also a function of a and b. Now I have those two variables. So its output is, instead of omega, in general, it's a function of a and b equal to that. So this is my wavelet transform. So for the wavelet psi, the wavelet has features. We can do operation in both dilation and translation. And the psi t is called the mother wavelet. And we do the dilation translation, that is its child wavelets. So this wavelet function, as we said, it's also a function of a and b. Okay, this wavelet psi t, you can think of any of those previous 8 different formats. You have this mother wavelet. A and b, a is a parameter for dilation. So you have this divide by a. Now, when you divide by a, it can be greater than 1, can be less than 1. So you shrink the wavelet or extend the wavelet. That is what I was mentioned. Then I actually shrink the window size or expand the window size. So it's not fixed, right? The entire window size is changing. And it itself is a small wave. Let's say I'm using this wavelet. So if you can think that you multiply this wavelet to your xt, which is also a windowed signal. Indeed, you windowed by the boundary of your small wave. It's windowed. Now, if you dilate that, you extend that. And of course, this window will be extended. If you shrink this wavelet, it becomes very small. And your window size is shrinked. So this is what we mentioned, that's the feature that we want. And then we divide by square root of a just to normalize that, make sure the energy doesn't change. This wavelet energy doesn't change. And then we have another parameter is B. B is the parameter of translation. Translation is simply we have T subtract B. That's the same as we T subtract tau. So you shift this window, shift the window that is centered at time B, not time 0. So we're doing both dilation and translation. So the continuous wavelet transform maps a function xt onto the time scale space. So that's two variables. One is A and one is B, because B is time shifting. So this is time scale. A is dilation, so that is the scale. This is scale variable. So we have here, that's doing the integration, as we said, integration of xt times this wavelet. Now this is not the mother wavelet, but the wavelet has changed with those two parameters A and B. It's taken in this format, and integration dt. So again, this is the part to replace my long wave, which is e to the negative j omega t, in my regular Fourier transform. This is, we can express that using an inner product. That's the inner product of two functions, xt and a psi sub a bt. In the product, you can think those two functions, xt and a psi a bt, are two vectors in the Hilbert space. So we are having those two vectors in the Hilbert space doing in the product. So this is basically integration over T. So sometimes people like to using that to concisely write a transform. So the wavelet transform output W, it's a function of two variables A and B. That's a wavelet transform on the function of xt. That's my signal xt. And that is the wavelet transform. So the wavelet transform, as we said, when you plot this picture as a function of A and B, now B is shifting time. And A is something that you are doing the dilation of this window. So with different A values, you kind of, you magnify the signal you're trying to analyze. So if the wavelet is really shrinked, you are only focused on a very short period of time. So on the x-axis, let's look at this A and a B. If you're going beyond, let's just doing some grid. People like to use some grid like that. It become denser and denser. And here, A is become denser and denser in this direction. So if you have look into somewhere here, this box will showing you the wavelet transform of something that you focused on A, and focus on this B, shift on to this B. So you're using that can really do a very nice job to analyze the input signal xt. So here is a wavelet transform output picture. So again, this is with respect to variables. It's a 2D picture. I'm drawing this on 3D is simply I'm not using a color code. The amplitude, I'm drawing the amplitude and showing in this 3D picture. So we have here, this is a function of translation. That's a function of B and a function of scale A. Now in short-term Fourier transform, this corresponding to tau, right? This corresponding to frequency omega. If you're using a discrete short-term Fourier transform, this corresponding to the time shift m, this corresponding to the frequency index k. Those are the similar. So in general, we got those two dimensions. One is translation, one is scale. And then using that, we can see the wavelet output in this picture. The wavelet output can do a very nice job for signal processing. Signal processing is not only we can focus on some details in frequency, but we can focus on the details in time. Okay, so that's I think that's good. So much I want to introduce of short-term Fourier transform and wavelet transform. Wavelet transform in particular is a very powerful signal processing tool. And I don't want to go too much detail into that. And in MATLAB, in signal processing toolbox, there are a lot of those functions using wavelet transform. And I will encourage you to try that after class. You just type in wavelet or check the MATLAB Simulink, that's a wavelet. There are many very good examples can show you how we can use a wavelet to process signals. Okay, so that's what I want to cover, a very brief introduction to this topic. Bye-bye, class.